Once again, thanks everyone for joining the session. My name is Dmitry Yanter. I am from Deutsche Bank Berlin Technology Center. And today we go through this topic of estimating project lifetime, how this may hopefully change your perspective of things that you look into strategically, and what can really impact and influence on your day-to-day work. So we'll go through project lifetime estimations of the problem statement and why I find this topic important. Then we go to some specific story about releases over maintenance, how these things are balanced between each other, and then we end up with summary of the first and the second one. Will give us an idea how to manage defects during our life cycle. So we start with the kind of very beginning. If let's say if I open some textbook about software engineering, software design, then normally you'll find something like that. You design your software, then you develop, you roll out, you maintain, and then decommission. This is something that is kind of taken from the textbook. The words may vary a little bit, but in the essence, I would put these three sections as something that more or less every software has to go through. And then they tend to say that we're kind of, as we go with the software, then the software tends to deteriorate. And in this case, I will propose you kind of a metaphor that during the life cycle of software or software product, we have to go through the stage of greenfield, where everything is fine, rapidly growing, to this deteriorated soil, so this kind of like a desert of legacy. And that the journey and going around this desert of legacy is something that most people not really enjoy about. And I think that this is quite a challenging task when it comes to implementing a change in this deteriorated area. So I tend to say that we somehow primarily focus along these three, primarily on development and on maintenance. So development and how to develop things, how to build the proper architecture. This is the thing that we mostly enjoy talking about, looking into, and this is where the most energy is put into. Maintenance is something that comes like in the morning after development happened. And maintenance, unfortunately, this is that we also have to discuss quite a lot, because this is part of our day-to-day life. Decommissioning is, to be honest, the topic that is very often behind the scenes. For instance, if we just look into most topics in conferences, then they are focused about development and some aspects about maintenance. So decommissioning stays behind the scenes. I've been in industry for about 17 years, and I started in research area, then moved to startup, and for about 11 years I've been in Deutsche Bank. And I would say that distribution of what we do is a little bit different. So most of work that you have to do in established enterprises actually have to maintain, and you have to kind of navigate around this desert of legacy or be close to the border. So maintenance is a very essential part of what we do. Development obviously comes on top, and decommission is something that we kind of face but tend to ignore a little bit. So in most cases, the inception, that's what we develop, what we write is kind of for ages. We'll develop it, probably will maintain it, but this is not us who will decommission it. So in many cases, IT projects and platforms, they live for quite long. However, in my experience, the closest cycle of development, maintenance, decommission was about 19 months. So within 2 years, actually, we developed something, we rolled it out, we saw it in operation, and we had to decommission. So actually, it's quite quick, and the experience itself, I would say, is quite eye-opening, if you wish. And I tend to say that industry is not quite good really at decommissioning things. And let me give you here some extreme, I would say, example, but nevertheless, it's very illustrative. So most of you, I think, know language COBOL. This is quite an old one. So this year it's about 64 years old, and it's still heavily used in production. So to give you some scale and some numbers, one of the recent reports that I read about usage of COBOL in production, they estimate that currently in operations and in production they use about 800 billion lines of COBOL code on day-to-day basis. So to give you a kind of a scale and measure, they estimate the whole Google code base of 6 billion lines of code. So you can imagine that amount of code, obviously not probably complexity of code and function of code, but the amount of code that is written in this 60 plus years old language in operation is quite significant, or I can say enormous. And another point to this fact that we're not like super good in decommissioning it is if I look into the trend. So if I open, let's say, some old textbook about software engineering that was written 25, 30 years ago, they will say that at this point in time, the estimated COBOL usage of 50 billion lines of code 20 years ago, and now it's about ridiculous 800 billion lines of code. So nevertheless, we're really not very good at decommissioning things, and this is unfortunately what creates not probably the best environment to work at, especially when you have to deep dive into these systems that are very not up to date, and they kind of represent legacy in their own. So let's try to put another perspective onto this. So if I ask myself, like, how long my project shall live, or what I'm really counting on it, the answer is not quite clear. Unlike, for instance, if you buy a smartphone or car or a watch, normally you will open this manual book and you will find a line where they say, like, for instance, this product is going to be used for 5 years or 10 years, 15 years, or maybe 1 year. And that actually gives some really good planning horizons and understanding how stable your product should be, and how basically you should work with it. In most cases in software, we tend not to put this definitely the official documentation on the line that this is going to be used for, for 10 years or for 10 months. But very often, even to ourselves, we do not make this kind of estimation. And think about it in the way that we have a lot of ways to estimate our sprints. So story points, t-shirt size, mandates, whatever. But we have no convenient, i.e. known to everybody, knowledge and way to estimate our projects. So luckily, we have already quite significant history, and we have quite a lot of data available publicly. And I propose you to look into this, to use GitHub repositories, archived GitHub repositories as a proxy for this. So actually in GitHub, you can say that now my repository is archived and it's kind of done. So what I did, I calculated active time of the repository, meaning that this is the time from the first commit until the last commit. And I calculated for top 1,000 most popular repos in GitHub. And what you can see on the slide is actually a histogram of distribution of how many repositories live for how long. You can see that the median, I would say, is about 6 years something. So this is kind of average between the most common repositories, how long they lived. Another interesting fact that if I put here another metrics, which is which I call here on the slide as maintenance day, which means that this is the the timeline between the repository was created, maintenance days, the repository was created, and the repository was marked as archived, not the time between first commit and last commit. So you can see that the chart moved a little bit to the right, and almost there were no repositories that were closed really very quickly. So this gives us another interesting insight in the ways we tend to look at our project. So despite the fact that you don't have any kind of commits, you don't do really any changes, it takes about a year or even more to say that yes, we're done. And that's to me echoes what we really face in our day-to-day life, even that we think that the project is kind of done, i.e., we are not really going to develop anything more. It's a separate decision, sometimes not quite easy to take, to say that now it's no longer active. We have to exit. What I also try to estimate is actually if there is any statistically significant difference in terms of what language, for instance, is on average gives you longer repository life, or if there is any significant difference in what language you choose. So I would say upfront that the results are not quite stable, i.e., if you choose like Java or non-Java, then it will guarantee some longer life of the repository and the projects. However, there are some interesting results that if I compare Java with all other languages, then there are a few interesting statistically effective and statistically significant observations. So Java, I would say, playing the same game or in the same league as C++, C#, Objective-C, and Scala. So meaning that they have more or less the same lifetime, and the lifetime or expected is on the slide. You will see expected survival function for Java repository, meaning that in 75% of the cases, your Java repository will live for at least 3 years. In 50% of the cases, so it's the median, the expected lifetime is about 4.5 years. So that gives some timeline. Again, this is timeline that we can find evidence for. So that's based on what you can see in the data of GitHub, and this gives you some kind of like scale. So what can be expected lifetime of your project? So whether it's 3 years, 5 years, 25 years. And another insight or techniques that I propose here to use is that, for instance, if you understand that your project is already 3 or 5 years old, then there is a very simplistic technique to say that probably we're in the middle of something, and if it's already 3 years in progress, then most likely it will last for another 3 years. So this gives you some kind of an indication where you are in the journey from this greenfield into the desert of legacy. At the very beginning, I said that most often we do not really see this expectations management, i.e., that my project will live for X years. However, there are cases where actually this is managed very properly and very explicitly. Like here on the slide, you can see Oracle Java SE support roadmap, which gives you exact date until which Oracle is going to support a specific version of Java. And I propose you to pay attention to the following. So you can see that there is, for instance, for Java version 11, there is about 13 years, to be precise, 12 years and a half, where this particular version is going to be supported. If you go down the line, that the next version is going to be supported for about 8 years, and the difference between first long-time support version and the second long-time support version is about 3 years. So actually, it gives, if you just go through all those examples, you find some interesting proportion that if you look into long-time support versions of the product, then maintenance time is about 4 times greater than release time. So meaning that they tend to release about every 2 or 3 years and support the product for about 8 to 12 years, and that gives an interesting mechanics and dynamics of how you can navigate through this journey. So actually, you can more or less understand how frequently you're going to release something, meaning that, and by releasing something, I mean that this is something that you have to support, and that gives, if for instance, if you release something, every significant every year, then you can easily calculate that probably something that has been developed within a year probably will have to support for another 4 years. Again, if you, like in this case, if you develop something within 2 years, then probably you would like to support a thing for about 8 years. So there is an interesting proportion. And if I go into some other examples, it can be, for instance, Ubuntu, or it can be Node.js, or it can be other software product. And interesting that this proportion is about the same. So in some cases, it's maintenance time is 3 times more than release times. Sometimes it's 5, but I would just put here 4 as kind of something that in the middle, and median value. Interesting that you find it quite consistently across multiple completely different projects and products. And what actually happens during this maintenance time? I would say that during this maintenance time, we are really in position to close the feedback loop. So we release something, and actually release of today is a commitment to support it tomorrow. And on the next morning after it really happened, normally we get starting feedback from production, and the most feedback from production actually comes as either in incident or in bugs. Another interesting takeaway. So if you look into your into statistics of open source projects, you will find out the distribution of the distribution of the slide of how many bugs are resolved versus unresolved. So I would say that more or less you can say that more or less it's equal number of resolved bugs versus unresolved. And interesting insight that most of bugs which are unresolved are kind of unresolved forever, so that you will have defects that were created years and years ago, and they are still unresolved. And this gives again this pressure deadline or understanding that your project will not live forever. It gives you some idea and impression that you're not really in position to fix in every bug, and you have to be really conscious about what you have to choose. In this example, I would propose you to use the metric that will help you to navigate through this journey to understand what you have to take, using this term, this called lifetime value. So very simplistically, the logic here is super straightforward, that if you have, for instance, a defect in your system, then it causes some maintenance effort. And this maintenance effort might be as simple as that you have to review it from day to day during your backlog reviews, or it might be time that users or support or yourself have to spend either to implement workaround or to investigate something or somehow to deal with the feedback that comes to you from production. So let me give you some calculation here. So in my example, just like illustrative example, defect occurs in 1% of user sessions. Then maintenance cost is kind of 5 minutes. Then user in my system tend to grow in phases, so I make rollouts, and expected lifetime of my project is about 4 years. And then what I would like to calculate is how much or how many hours or how much time this particular defect, this illustrative defect, will cost for me during the lifetime of my project. So to do this, I just calculated this function of cost over time. And first insight is that as users tend to grow linearly, then cost of maintenance actually rises faster than linear when the users are stable. And here I kind of model scenario that I start with some small user population, then I roll out to some other user group, then I kind of stabilize it, and then I roll out my product to the group, to my target audience. So you see that even when I have a stable number of users, the cost tends to rise. And here in this case, when the number of users is stable, it rises linearly. When the users rise, then actually maintenance cost tends to rise non-linearly. So this is about so it's square of t. An interesting calculation gives me the following answer. So in my super simple case, where again I will repeat here that probability of occurrence is about 1%, and for every occurrence I have to spend 5 minutes to react on this. Lifetime value of this particular defect will be about 117 hours. And in this case, actually, so it's more than a week to work, and it's almost 3 weeks of working time. You think about like that, such a small issue can cost you, at scale of your project lifetime, this enormous time spent to maintenance. In this case, I would say that the best strategy to address defects is to fix them immediately, so that you can fix them directly somewhere when it starts to grow, and actually you don't waste those hundreds of hours until the project lifetime. And in this case, it my PA, for instance, to fix this bug, it may take 1 day or 2 days or 3. It gives you a tremendous return on investment. And I wanted actually to verify if this hypothesis that you have to deal with the bugs in the way that you should actually fix them more or less immediately, if there is some evidence of it. So to do this, I analyzed again open source data with prints and issues and story points and time to resolve. This is quite an interesting data set that contains about 500,000 records about different issues across multiple projects. And this is basically the distribution of days to resolve for those projects. And you see that the distribution of days to resolve tend to be very, very linked to the left. Actually, it means that it's indeed in many projects, in many open source projects that were part of the data set, people tend to resolve bugs as fast as possible. So the numbers give you that again, median value is about 12 days to resolve. and 75th percentile is about 71 days to resolve, which kind of give you an impression that most of the bugs are resolved within first 3 months, i.e. day when these were created and these were closed and released. So actually that somehow proves that in many cases, people tend to follow the strategy that bugs really needs to be resolved quite quickly and fast and as soon as possible, or actually you either resolve them quickly or you make a decision that they will be unresolved forever. So that's an interesting insight, right? So when you get a new defect, you have to kind of understand in which bucket you have to put it. Either you take it and resolve it, or you keep it in forever. And that's not an easy, not an obvious action to take. In many cases, what I saw, we just like put the bugs in long list of backlog, and from time to time review them. But I really encourage here to make as many decisions as possible, whether you really plan to fix those defects that you get from production, or you keep them kind of unresolved forever. So this will save at least, for instance, time to maintenance them. I need to go through them and to review them from time to time. And interesting that, again, if I look into distribution of how many defects projects tend to keep in their books, you see this steady growth. So actually project keep to have quite a long list of unresolved bugs, and you can see that it's growth, and at some point it just can reside on some stable level. These are charts that I made from the data source. You can see that these are quite impressive projects that were there and were live for more than 10 years. So maybe to sum up this use case and this story, the best way and best means the most the way that they saves a lot of energy and time to manage defects is understand whether they should be fixed quickly or never. So they kind of should be quite deterministic. So they either go and fix them, or you stay there those defects forever in the system and kind of live with them. And if you look into some long-running project, then you easily can have some thousands of unresolved issues that are kept into the backlog. So we are wrapping up. I hope that overview was helpful for you, and I really encourage you to think about your projects not just into this greenfield area, but actually how you navigate till the end. And hopefully, if we manage to work with our project, with our software, and with our platforms through the whole lifetime, that makes this journey across this desert of legacy not as painful as it is today. Okay, thank you very much for your time, for attention, and I'm ready to take the questions. Okay, I can see the question in the chat. Which open source project GitHub you have analyzed? Yeah, so all these projects, they are open, so definitely they're not private, so open, and I just filtered them by number of stars. So I took 1,000, the most to give the first charts of for distribution was 1,000, the most common one, to find some differences and to understand the Java survival curve. I took some more thousands to get the distribution. Interesting nuance here that, for instance, if you take active projects in GitHub, again, most popular ones, you will find quite similar distribution of time. So it will not be dramatically different. So you'll get maybe not 6 years, but maybe 7 years, but the distribution will be quite similar.